sooner. You know that I'm talking and I'm presenting and you don't see something, then that's the chance for you to say something. Thank you, though. All right. So what I'm trying to say here was, you'll see it. If somebody was walking, oh, let me go down and click it. If somebody was walking in a straight line like this, like I had said, just walking along this path, and if the x and y axis was like this, the original drawing showed that the y axis went straight down and the x axis went this way, then you'd say they're walking in one dimension because all their motion is along the x axis. You'd say their velocity is a horizontal velocity because it's referencing the x axis. But then I said, well, what if our xy axis was kind of tilted a little bit and your y axis went this way and your x axis went this way? And the person still decides to walk in the same direction as they had before in the first image. Are they still walking in one dimension? Is it still considered one-dimensional motion? Well, again, it has to be compared back to the xy axis. You'd say technically not, because that motion that I just drew here, this velocity vector, is not all along the x-axis. It's not all along the y-axis. It has components. It has a component right here, which is parallel to the x-axis. It has a component right here, which is parallel to the y-axis. So that's the y component of the velocity. And therefore, you'd say that's actually two-dimensional motion. So I'm just pointing out what two-dimensional motion means. It means that you have motion through some xy axis coordinate system that involves some motion along the x-axis as well as some motion along the y-axis, called two-dimensional motion. What's a more concrete example? A more concrete example with respect to what we're going to be talking about is an object shot sideways off of a cliff. This is the ground down here. Originally, all of the motion and all of the speed is horizontal because your xy axis is 99.9% of the time like that. It's what you call an absolute xy axis and an absolute coordinate. Absolute means the x is the way you would always expect it to be, flat, and y is straight up and down, absolute coordinate system. If it's turned a little bit, we call that skewed. There are some applications in physics like the inclined plane, which we haven't gotten to yet, where you actually skew the axis, but we'll get to that later. The xy axis gets turned. But based on this xy axis, all of this speed, when this is a rolling ball, this is a rolling ball that's about to roll off the table, all of the speed at this point is horizontal because it hasn't come off the edge yet. So in that moment, you'd say it's one-dimensional motion. But a little bit later, it's going to be moving like this. And over here, it's going to be moving like this. And over here, it's kind of moving this way. In all of those cases, it's now moving in two dimensions. Because this is a velocity vector. All these things that I've drawn are velocity vectors. The velocity vectors are always tangent to the path. So the curved path that goes like this is called the trajectory. It's a curve if you're moving in two dimensions in this type of problem. And the velocity vector is always tangent. So again, on the side, if this was the trajectory and this was the ball, velocity vector is always tangent. 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 So in that instantaneous moment, you're drawing a picture of its position, and someone says, which way is it going? In the direction of the velocity vector, which is always tangent to the trajectory at that moment. These are all velocity vectors. So my point is, if we looked at just one of these, let's say this one here, let me erase a little bit of that, draw it a little neater. You'd say it actually has two-dimensional motion, right? There's this velocity vector here, which I had drawn before, has an x component, which we call Vx, because it indicates that it's along the parallel to the x-axis. It indicates that that velocity is going to cause the ball to drift rightward as it continues along the trajectory, right? Because in this moment, its horizontal position is here. But in this moment, the horizontal position is here. So it's definitely moving sideways as it falls along the trajectory, further and further from the edge of the table. That's what Vx is indicating. It's telling you how fast is it moving along that x-axis. It's not actually moving along the x-axis, it's moving along a trajectory. But we have to now start thinking in two dimensions, which is we have to take this complicated curved motion and think either only about the horizontal motion, like the position here. It went from this spot to this spot to this spot. You're essentially projecting that position down to the x-axis. It's almost like the shadow. If there was a shadow, if the ball, as it went along the curved path, had a shadow, if there was a big light on the ceiling, you'd see the shadow physically moving across the floor until it struck the floor. And Vx, as I've drawn here, would be the speed of that shadow. It's actually showing you how fast it's moving horizontally, because the shadow is actually just the horizontal projection of that thing's motion. So that's Vx. Where would Vy be? Right here. Because this downward component velocity, you know, is causing its position to drop, right? From here to here. These marks here are referencing where the ball is vertically. You'd see that it's vertically dropping for all of these positions. And that's what Vy is indicating. There's a motion in downward direction as well. And it's perpendicular, it's this parallel to the y-axis. So this is just for setting up, framing the whole topic of 2D motion. And now we're going to look at it in this video. In this video, which is not there, which is here, there's a ball. And it gives me the ability to click with a little dot, like use my mouse, and click in the center of the ball. And essentially what it does is it flags the position of the ball in that spot. And soon as I click it, you'd see that it leaves a dot. For those of people that are in class, harder for you to see, so I'll zoom in. Each time I clicked it, it advances forward to the next frame. Videos are usually 30 frames per second, just your typical video frame rate. It means it's taking 30 images per second while you're recording on your phone. When you want to watch it back, it just stores all those videos, all those images rather, as a sequence of images, and it just shows one, and then 1/30th of a second later it shows the next, and 1/30th of a second later shows the next, and it just goes so fast that your brain can't even recognize that it's just a flip book. That's the concept of what a video is. And so my point is, each time I click the ball, it's just advancing to the next image. So before I get into the projectile motion topic, which happens at the edge over here, once it goes off the edge, let's just talk about some physics of kinematics relating to 1D motion. So the first comment is, there's not going to be much friction on this table. It's a black science table, almost exactly the ones that are in this room. Smooth, very low friction. That ball is probably one of the marbles that you've seen in my classroom. A ball bearing. I don't have it right now in front of me, but steel ball bearing. Smooth. Smooth on smooth means low friction. And it's rolling. It's not sliding. Sliding is like when you slide a book across the floor and you hear that slide and you see it slowing, and it stops. That's called sliding friction. In that case, the frictional, dragging, sliding effect of the cover of the book over the floor creates heat because it's friction, right? Rub your hands together and you can feel the heat immediately. So any sliding of something across something else, even if it's a tire on the asphalt because they just locked up their brakes and you see a giant black skid mark, that's evidence that that was happening. That dragging frictional effect creates heat. That's why it turns black. And that heat is energy. Heat is energy, right? So conservation of energy says you can't take some of your energy, which in this case is the kinetic energy of maybe a car that's trying to stop. If it's taking some of that motion energy and turning it into heat, then some of that motion energy has to decrease. If it creates 5 joules of heat energy as it slid and created a little heat, then the kinetic energy of that vehicle must have dropped by 5 joules because it's taking that kinetic energy and transforming it into heat energy. And every moment that would keep happening. A little less kinetic energy of the car slows down even more because it just turns some of that energy, motion energy, into heat until it stops. That means all of the kinetic energy of the car has been converted to heat in the atmosphere, in the air, and in the asphalt. That's not what's happening here because this is a rolling ball. Things that are rolling is totally different than something that's sliding. You can take a bowling ball and roll it in our hallway, just the smallest little nudge. Guess how far it would go? All the way to the other end of the hallway, 200 feet. That indicates there's almost no friction. There's some, it's just such a small amount. Balls that are rolled, the physics of rolling, there is some friction, but I'm going to tell you it's really tiny. It's a really tiny amount of friction. It's called rolling friction. That's a small amount. With that in mind, this is a video that you'll see a frame at a time in a moment of it moving across the table, and then it's going to go along there. But we're going to talk just about the table spot first. If I continue clicking, which I'm going to do with my mouse right in the center of the ball, and when I do that, it makes a blue dot and advances it to the next frame. I ask you to consider, what do you think the spacing is going to be like for this ball as it marches its way across the table one frame at a time? Choice A would be, let me do that. I have to remember, because I did that a number of times. I never learned how to undo the dots. So give me a second. Oh yeah, I have to, it's a pain. Oh, I see, because I'm doing that. Yeah. I have to switch the mode over to that. Let's see. I don't know if it will let me. Yeah, it does. Okay. So as this moves across the tabletop, do you think that the spacing of each dot will look like this? I'm not intending to make them smaller, like they're all the same size. Do you think that the motion as it rolls across this table will look like this? Or do you think that the motion of the ball as it rolls across the table will look like this? Just remember that this is called a motion map, and it means you're showing the position of the object at an equal interval of time. Usually in freshman physics, we say every second we're going to take a picture of where the car is and we'll draw a picture where the car is. You probably remember that from 9th grade. But clearly not 1 second. This is only 1/30th of a second. Who cares though? It's a time interval. It means every 1/30th of a second, you're snapping a shot of where it is and you're drawing every 1/30th of a second. Whatever the interval is, you just keep moving forward in time by that interval, drawing where it is. Which one do you think it will be and why? Remember that when you answer that question, that's called the claim. AP Physics will refer to it as the claim on the AP exam. And to get full credit, you have to provide what they call the justification. The justification, the reason, the rationale, the support for your claim. One without the other often gets no credit. So think to yourself, which one do you think it would be? And what would your justification for that be? After you thought about it, let me know. At home, you can just unmute yourself and tell me. But here, or you're here, you can just raise your hand and tell me. Oh, wait, I know you, I'm anxious for that. But before you tell me why, we have a B. Anybody else want to tell me what they think? I just want to get a poll on what you guys think. Yeah. B, you have an opinion?
B.
B, who was that?
I say C.
You guys all like B? How about Darius? And how about here? B, wow, okay. Let's go back to Emma. Why do you think, because she was the first, why do you think it would be B?
There's no friction.
Yep, so she's saying since there's almost no friction, then because there's no friction, why can't it be C if I play devil's advocate here? It's true that there's no friction, but why does no friction mean that it can't be C? Go ahead, yeah. Good, so she said friction slows things down. So if it's friction slowing it down, why can't it be C? Why is C not a slowing down? Go ahead, keep going. She said because the spaces are greater, which indicates it's speeding up. Nicely done. So you're following a train of thought, and if you were writing, you'd have to say all of those things. One thing, because of that, this, because of that, this. So the person that's reading that says, boom, all in one nice package. Full credit. Yep, so you wouldn't be C because this indicates something is speeding up because it's covering a greater distance each interval of time. And speed is how much distance you cover in each interval of time. Since it's getting wider, it means it's covering more distance each interval. The speed must be increasing. Why can't it be A? Somebody else, though. Maybe at home. Hold on, actually. Let me increase the volume of... Okay, somebody at home. Why can't it be A?
Because the friction isn't great enough to affect the speed.
Good. So the student at home said because the friction isn't great enough for it to affect the speed. What in A indicates that the speed is being affected? Jaden. Is that
The
Jaden?
spaces between each interval that is taken is slowly becoming closer together.
Which he says each of these are becoming slowly closer together. So what is that? Since you see that, what is your interpretation of that?
It means it is decelerating.
Ah, good. It's decelerating, slowing down, which doesn't match with the idea that we said there's almost no friction on the table, right?
Yes.
Good. So let's just see what happens. I'm going to advance it forward by just continuing to, I hate having to do this each time. It's a pain. Sometimes I forget. Here we go. I don't know if this is going to work. Nope. Wait a second. Should have worked. Oh, do I have to go back to? Maybe. Yeah. Okay. Let's give it a try. Here we go. And my dots aren't perfect. This is a user. The user input is me trying to put it in the center of the circle of the sphere and click it. Not going to be perfect. But it'll be close. Okay. So what are we seeing evidence for? Didn't want that there. What are we seeing evidence for in this photo? B. We're seeing evidence for B, right? They're equally spaced. Now, if I were to say, and by the way, which we call constant speed motion, right? This is evidence that the speed is constant. Now, if I were to, I just put my pen over here. Now, if we were, and now I have to, sorry. Back to here. Back to here. Back to here. Now, if I were to ask you to draw a, why does that not work? Now, if I were to ask you to draw, still not working. You have to come over here. Here we go. A free body diagram for the ball while it was rolling. What would you do? And try it. Try it for yourselves. Draw a free body diagram. Now you'd have to think, oh, free body diagram. Boy, remember that. That was a long time ago. Free body diagram for the ball in one of those positions on the table. It doesn't matter which, but just imagine pausing it. We've already have evidence for the fact that it's moving at a constant speed. And they say, draw a free body diagram for the ball while it moves along the table. Remember, the free body diagram shows the vectors, which are force vectors that indicate what type of force. So you have to label the vector to name the vector, identify it with some sort of word or common symbol used in physics as a notation for that vector. I'm not going to say what they are right now. Just see what you come up with. It's been a little while. And also, the vector has to point in the direction that you think that force is. And also, if you're drawing two force vectors on a free body diagram, and you think one of them is a much stronger force than the other, then that one that's a much stronger force should be a longer vector, and the one that you think is the weaker force would be the shorter vector. The magnitude length of the force vector indicates how much force we're talking. That's how you qualitatively represent force, magnitude of force, by the length of the vector. To try to draw a free body diagram for the ball while it's on the table, while it's rolling. And often the AP exam would call that FBD, for free body diagram. Sometimes they'll say, draw a free body diagram. Sometimes they say, draw FBD. And at that point, you'd have to be like, I know what that is. We've done that because this is the beginning of the year, but at that point, you've gone through the whole entire year. We'll be referencing FBDs an awful lot this year. So who wants to suggest any forces that you believe are acting on that ball? Any forces that you, who said what?
Gravity.
All right, gravity. Which way should I draw it?
Down.
Down. If I wrote the word gravity, I wouldn't get credit on an AP exam. They'd say they'd say, I know what the kid meant. And they'd say, I know it's right. But they'd end up saying, that's not really the notation. We wouldn't write the word gravity. So is there another way? Usually we have to use the symbol F to represent force, and then a little letter underneath the F to indicate what kind of force we're talking. So F. Gravity would be what?
G.
G. This is what you'd see in a textbook, force of gravity. Other textbooks, I will point out, put W. Because what does W stand for? Weight. The force of gravity is your weight. The force of gravity on this ball is the weight of the ball. So I do know, because I know people who work for who grade these when that time comes at the end of the year, work for College Board. They accept W and they accept FG. They say if their student wrote gravity, they wouldn't give credit for it. Just letting you know. What other forces? Yeah. Yep. So because if you're not sure, because you could always write gravity. Unless it's some problem where it's like an astronaut is floating in outer space, far, far away from any planet or any star, and there's no gravity out there. Draw a free body diagram. All right, for that one problem, you wouldn't draw for gravity because they just said there's no gravity out there. But 99.9999% of all the other problems, there's always gravity. Let's always start with downward gravity. Then if you were unsure, just think, what else is it touching? What is touching the ball? Because to touch means to apply a force. You can't touch something without not applying a force to it. So what's it touching? What's in contact with the ball while it rolled? What is it? The table, exactly. You'd see that the table is technically touching it. Which way would the table be pushing it? Up. That's what Emma was saying. There's a normal force. N stands for normal. I know you couldn't see that, F. But this stands for normal force. A lot of students do say natural force. It's actually called the normal force. The normal force is a force that comes from anything that you're sitting on, anything that's supporting your weight. Your chair is providing a normal force to your butt. The tile floor is providing a normal force to your feet because they're not falling, right? If your chair could just stay where it was and I could rip away the actual tile floor, your feet would drop a little bit. That's evidence that those tiles are supporting your feet right now. They're preventing it from falling. That means which way are they pushing on your feet? Up. What do we call that force? The normal force. The car is driving along the road. Now we don't have a table, now we have the asphalt. Which way is the asphalt applying a force on the car as it drives on a flat road? Up. It's called the normal force. Anything that you're resting on that's supporting your weight is always an upward force called the normal force. Now, my point is also, I couldn't draw this small. That would be wrong. If I drew it like this is indicating to the person grading that you think there's more weight force than the normal force. If that were the case, that means you're indicating that there's an extra amount of downward force compared to the upward force, which means you're indicating that there's a net downward force. The net force is down, if you drew it the way I've just done here. But there is no net force. This is correct, the way I drew it here. What is the net force? Net means you have to add these vectors up.
Zero.
Zero. Yeah, it's good job. It's vector addition. What is this plus this? The same vector addition we've already spent quite a bit of time doing. Same vector addition. You say, yeah, but how does that work if they're like one's up, head to tail? So this is the head. So tail right there, down. Where's the resultant? How long is the resultant? Those I just drew each one added to the next head to tail method. How long is the result? If I went like this and like this, I'd say this is the resultant. Oops, right here. But I drew it like this. What's the length of the resultant? 0. There is no resultant. Yep. This is a vector addition problem that provides an answer of 0. Like, what's 7 minus 7? That indicates there's no net force. The net force is equal to 0. That's what this picture is trying to imply. There's a full cancellation. If the weight of the ball was 1 pound, then the downward weight of the ball is 1 pound. The normal force is 1 pound up. But they don't want to talk about pounds because everything has to be metric system. So if the weight of the ball is 1 Newton down, then the normal force from the table is 1 Newton up. 1 Newton up is plus, 1 Newton down is minus, 1 minus 1 is 0. So there's no net force. Then I'd ask, okay, if that's true, what is the acceleration of the ball while it goes across the table? Haven't even gone into the projectile motion part yet. With all of this said, what is the acceleration of the ball while it rolls across that table with equally distant dots in its motion map? Yeah, 0. Yep, there is no acceleration. There's no acceleration, meaning it's not gaining speed. It's not slowing down. It's not speeding up. We already said that out of the choices that are on the board, it was B. It's not A, which would have been slowing down. It's not C, which would have been speeding up. There's no acceleration. And sometimes you'd put an X here to indicate horizontal motion, because the ball rolling on the table is technically a horizontal motion. Does Newton's law support that claim that if the net force is 0, that the acceleration is 0? Yes. It's which one of its 3 laws? First law, the law of inertia. An object in motion stays in motion. An object at rest stays at rest, unless acted upon by some net force, some extra amount of force in a certain direction. And let me comment that a lot of students drawing the free body diagram like we just did would do this and then do this. Applied force forward, or some sort of forward force, because the ball is rolling to the right. A lot of students who get the free body diagram wrong are losing points because of that. There is no forward force. The only other molecules that are in contact with the ball, other than the table, is the air. And if the ball's rolling to the right, the air resistance force is actually the other way, because it's like friction. If you're rolling to the right or sliding to the right, all frictional forces are always in the opposite direction. In the real world, there would be some air resistance on that ball. But in their problem, they'd say, assume there's no air resistance, assume there's no friction, because they don't want to overcomplicate the problem. So I'm pointing out in the real world that would be there, but it would be a very tiny amount of air resistance force. But if you've already thought about that one, and the frictional force from the physical contact with the table is also minimal, then for the students that have FA, I'd say, who is that? What object is that? Name FA. Is it a person? Is it an air molecule? You say air molecules? Oh, that's air resistance, that's backwards. Table, it's friction, it's backwards. Gravity is downwards. So who is this? Who is FA? Students finally realize it's not there. It's a misconception. This is the inertia, the concept that the ball that's rolling will continue rolling on its own forever, no force necessary. In outer space, for example, if you threw something in outer space, far, far away from planets where there's no gravity, no air, there's nothing out there. You toss a ball as an astronaut, the ball will go in a straight line forever and ever and ever, never lose any speed. It'll, for all of eternity, just continue coasting at a constant speed for the rest of eternity. And if someone said, what force is continuing that to move? None. There's no force necessary to cause that thing to move. Newton said there's only force, a net force is only responsible, or net force is only needed to slow something down or to speed something up. That's all he said. He said if you are in outer space and there's no forces to fight against, then there's no forward force necessary. There's a forward force to get it moving when you throw it. You have to apply a forward force, but once it's coasting, it'll just go forever like that. There is no forward force. So I wanted to point that out. And so since we're recognizing that this is not there, and the net force was 0, and the acceleration is 0, then his second law comes into play. Newton's first law was the one I said, an object in motion stays in motion, an object at rest stays at rest. It's the law of inertia. The second law is Newton's second law, F net equals ma. Does this support these two claims? Do those all fit together properly? Is there a connection between the statement F net equals 0, the statement A equals 0, and then the theory that F net equals ma? Are those all harmoniously in agreement, or is there some conflict there? Well, if the net force is 0, acceleration is 0, no matter what number I put here for the mass, will it be a true statement? 0 equals 0. Yep. So it's in agreement? Absolutely. That's something to recognize, that if they said, what formula supports this? You'd say Newton's second law, F net equals ma. If you're giving me a problem where the net force is 0, then the acceleration is 0. 0 acceleration doesn't mean it's not moving. It could be. If I'm standing still and not moving, and someone said, what is your acceleration? 0. But what about when I drove to work today? I just stayed at 60 miles per hour the whole time. What was my acceleration? 0. I wasn't changing my speed. Both of those scenarios involve 0 acceleration. Okay, now we wonder, what would the position versus time graph look like for the data I collected as it rolled across the table? Position versus time. The horizontal position is what I'm referring to. As it rolled, I'm going to erase all this. So if I decided to take an XY axis like this and say, this is some position X1, this is position X2, this was position X3, this was position X4. And let's just say we did that essentially, but my point is if we had collected data and said, this mark was the 0 meter mark, and we actually collected data and said, okay, on the side, X1 was, 2 centimeters, X2 was 4 centimeters, X3 was 6 centimeters, and it would have to be equal intervals because you can see those dashes are increasing in equal intervals. And the question now is, if I graphed that, horizontal position versus time, what would that data look like graphically? Assuming that it started at the origin, so start x initial was 0. You try to sketch it down for yourself. Think, what would that graph look like? It's a common type of question for free response. If they give you something, they say, here's a blank graph, sketch what you think it looks like. Try it. What do you think what we say x versus t, position versus time? But horizontal, we're talking horizontal motion. Once it goes off the edge of this table, then we have to start talking about the vertical motion. Discussion changes at that point. But right now, we're just talking about the horizontal motion, x versus t.
Mr. Kurzak, do you want an answer?
Sure, go for it.
It would be a linear relationship.
Yep, linear relationship, because this is linear data, right? Something that increases in equal intervals per some amount of time is linear. Good job. Yep, it would look like this. Let's just see, and that's the cool part of this tool, this video analysis tool that I'm using. It created a graph already. Some of you might have seen it, and I didn't mean to have it on the screen. I wanted to hide it first, but why do I always lose? Back to the mouse. To go back over here. There's the data it collected. The vertical axis is the horizontal position, and the time axis is the time. How did it get that data? Every time I clicked, I made a blue dot, and the computer program has been programmed to measure the distances between each blue dot, figure out how much time has elapsed in the video between each of those blue dots, create a data set in the background, which you don't even see, and plot it out for you. So it's linear, right? What equation would go with this? What formula would model this data? Position versus time. It would think, okay, kinematic formulas, it would have to have a position, which is a distance in it, and it would have to have a time in it. Which of the big three formulas, there's only one, has both of those things? Now I have to go back again. Let me, yeah. So there's this formula. There's this formula, what I refer to as the big three. And so do many textbooks. And this one, these are the big three. Which one has position in it and time in it? Because our graph is position versus time. Yep. Yep. Not this one, because there's no distance in this one. Not this one, there's no distance in this one. These are distances. Position is a distance measured back to some starting point. This one. All right, what would we take the initial position as? Well, look at the graph. What is the initial position? It's a position versus time graph. The initial position is the y-intercept. Right? Y-intercept is always your initial value at time t equals 0. It's pretty close to what I want it to be. It's not exactly what I want it to be because I had some error. I had a few data points set. You can see way down over here. Threw it off a little bit. But what is the y-intercept pretty close to? Yeah. Yeah. What is it? Oh, I see. Yeah. So I thought that was the 0. So that's not correct because I don't know. It must not know exactly where the 0 mark is. What should the initial position be? Usually when you start the video, you'd say right at that starting frame, that's where x initial is 0. It's the starting point. So my point is, I think the software isn't fully sure on, oh, that's why. See where the xy axis is? This is the computer's xy axis. It should have been over here where I wanted it to be. Had it been over there, it would have been 0. So x initial would be 0. And now you're left with v initial t plus 1/2 at squared. What is the acceleration of the ball as it rolled on the sideways? We already concluded what the acceleration was from Newton's second law. What was the acceleration of the ball while it rolled sideways? 0. It's constant speed motion. You plug 0 in there, that term's gone. What are we left with? The final position equals, and you don't even need the initial value because was the velocity changing as it rolled to the right? The direction wasn't changing. The speed wasn't changing. Those were all equal distances. Usually we have VI here to indicate initial velocity because later it might be some different value, and we don't want to confuse those. But when you're talking constant speed motion, you can just drop the I and say V times t, right? If you solve this for V, distance over time, you're back to 8th grade physics. Speed is distance divided by time, right? That's exactly what that is. So this is the formula that models that, right? It means that if you knew the physical velocity, which, how would we work out this velocity? My comment on that. You'd have to take one little chunk, like here, and figure out what is the change in position between those 2 points. You'd have to say, okay, this was the, I don't know, 2 centimeter mark, and the next line was the 4 centimeter mark, and therefore delta x would have been 2 centimeters, because it's the difference between those 2 points, 4 minus 2. And then you'd have to know, what is delta t? The time in between those two. I don't know how much time is in between them. If it was a 30 frame per second camera, it would be 1/30 of a second. And you'd have to divide by delta t. That's how you would solve for the velocity, right? V is delta x over delta t. So you're seeing how that would come into play, that formula, from a practical experimental point of view. You just have to pick 2 images, figure out what is the distance between those 2 images and how much time elapsed between those 2 images. It's constant speed motion, just delta x over delta t. All right, I'm going to erase all this, and we finally get to leave the edge of the table. That's important stuff to use, I think, to see how all that plays out. So now I'm going to continue clicking on my ball, and each time I click on my ball, it's going to keep doing the same thing. It's going to put a blue dot. It's going to continue tracking the horizontal position. This right here says x in meters. It's going to continue tracking the horizontal position. The data that's here is the data that was on the table, rolling on the table. But once it starts going into free fall and going along this curve, I'm going to continue clicking dot, dot, and it's still going to be referencing the horizontal position measured from this line. You can see it as a yellow line there. That's the x equals 0 line. And so at all points, it's still going to be marking the horizontal position. It's going to keep adding data points to our graph. So here becomes the question for you to think about. As I do that, I'm about to do it in a moment. Start clicking, clicking, clicking. It's going to start falling from the edge of the table. What will this graph do? Well, the new data points that appear in here, they're not going to appear over here. This is the data that came from the table. Right? It's just spread out over time, on time. Will the new data points that come in while it's falling cause it to curve up? Which you might call a quadratic effect. Choice A. Do you think the data points will continue straight along that line, which you call a linear effect? Or do you think they'll start kind of curling in the downward direction, which you might call like a square root effect? Something kind of like this, which we'll call choice C. To think to yourself what you think the answer to that would be. Those data points will start to populate on that graph as I start clicking, but having you make an educated guess. Let's go ahead and call it a hypothesis. Will the data points physically start coming in like this? Will the data points start coming in like this? Will the data points start coming in like this? As we track the horizontal position while it falls. Ooh, hard question.
Mr. Kurzak,
Yep.
I believe it would be C.
All right, we have somebody that has put their vote in. Thank you for your vote. C. Anybody else at home that has a vote? Emma. Okay, B. Anybody else?
B.
Who is saying B?
Zoe.
Zoe likes B. What do you like, Ashley? B. B. Anybody else? Who's left at home? I don't even remember. Sorry. Carly's. Isn't Carly still there?
Yeah, I think B.
You think B. All right. So you can think to yourself, why do I think that? I'm not going to ask people to defend themselves right now. But if you were writing, you'd have to. Your claim is that I think it's B, and then they'd say justify why you think that. Just think to yourself, why did I choose whatever you chose, A or C or B? What would I write if someone told me to write down why I chose that? Just think to yourself, and then let's see. All right, I'm going to go back. I'm going to erase. Erase. Yep. All right, and now I'm going to just start clicking right at the center of the ball. That's not the right tool, though. It tells me. Here we are. Oh, sorry, one more second. I'm going to like that. Oh, I just made an error with that one, sorry. And I don't know how to undo them, unfortunately. So there'll be a couple, maybe a couple errors. You can see them being added to the graph on the top right. All right. Wow. Interesting. What does the slope of this horizontal position versus time graph represent? What does the slope of this represent? Yeah.
Represents the velocity.
Yep. Two people said at the same time, one in class, one outside of class. Yep. This is the velocity. You can take any two data points on here, draw a triangle. Remember that this was the X graph and this is the T graph. So that means the distance between here and here is delta x, the change in position, displacement. This is delta t. Back to the formula that I had just written a moment ago, delta x over delta t, that's v. That's the slope of this graph. Did the slope of the graph change as a result of being on the table compared to being in the air? You can clearly see it did not. The slope of the graph maintained itself. But what can we conclude? What actually didn't change as a result of falling off the edge of the table? The position changed, the horizontal position changed. It kept getting further away from that yellow crosshair that's on the edge of the table. The acceleration horizontally, I don't know. What about the velocity, the horizontal velocity? It didn't change, exactly. That's the surprise. If I were to draw these lines in here for you to see just those horizontal distances, and then compare that to over here, not perfectly done, but are they any different? No. See, that's a huge thing for people. Like, that's crazy. Like, so a result of falling along a curved path, even though gravity's pulling you down, that doesn't affect how far you move sideways. I'll let him in just 1 second. That doesn't affect how far you move sideways in some interval of time. That's right. Why does the downward gravity force not affect the horizontal motion? Because those things are independent of each other. You might have read about the independence of motion. Vertical forces do not affect horizontal motion. Vertical forces affect vertical motion. Horizontal forces affect horizontal motion. Were there any significant horizontal forces that we discussed? We go back to our free body diagram. We had the normal force up and gravity down. We said the frictional force was minimal. That would have been horizontal and to the left. The air resistance force was minimal because it's a fairly aerodynamic thing. It's a little ball bearing. There were no horizontal forces. Newton would have said, of course. That's why the horizontal speed isn't changing. Because if it was changing, you'd call that a horizontal acceleration. And you'd say there is no horizontal acceleration because there is no horizontal forces. He'd say, that's my second law, right? You go, that's interesting. That's pretty cool. I'd note that down. You can note it down. That's the main idea. That was one of the main ideas in what you had hopefully read. I think they talked about this. The fact that the horizontal speed does not change during a trajectory. The trajectory can be literally a football, which we haven't done. That's more advanced. We'll get to that another day. Football being thrown across the field, a true like up in the air and then comes down. Even in that case, the horizontal speed doesn't change. The football literally moves equal distances forward down the field each second, regardless of while it's going up or coming down. Its shadow, if it was a sunny day, the shadow would move across the football field at a constant speed. And even in this case, doesn't matter if it's on the table or in the air, the horizontal speed does not change because there are no horizontal forces. Only the vertical forces are affecting its motion. So let's dive into that. How has the vertical forces that we've identified in our free body diagram on the right side of the screen, how have those vertical forces affected its motion? Let's draw some lines in here just to kind of see. Every blue dot, I'm going to just draw a horizontal line through it. So you can see that when you're looking at the first set of lines that are vertical, I drew vertical lines originally in there, those were all equally spaced, indicating that the horizontal speed was constant, even once it went airborne. And the ball is at these spots. That becomes hard to see. There's the actual image of the ball right there. This is called the trajectory. Horizontally, it's moving equal distance each interval of time. Horizontal speed is constant regardless of whether it's on the table or in the air because there are no horizontal forces. Acceleration horizontally is zero. It's maintaining a constant horizontal speed. But what happens vertically when you look at these ones? What's happening to that's a motion map. It's kind of another form of a motion map. What's happening to the vertical position? It's speeding up. Yep. That's in agreement with our typical motion map for something that's speeding up. Each interval of time, it's falling even greater and greater distances. You'd say, well, that's kind of what we have here, right? If I drew this one here, and then this one here, and then this one here, you'd see that these distances are getting longer. In equal amounts of time, it falls yet a further vertical distance than it had in the previous interval of time. You'd say, oh, that means it's accelerating. Vertically it is, and this is where there's the challenge. That's why 2D motion for a lot of people is like, God, confusing. I have to think about all of these things for the horizontal, and then I have to think about all the same things for vertical motion. Like, yep. But you'll get used to it. Don't worry, you'll practice it. But it's hard. You have to now either have the X horizontal glasses on while you look at this, or the Y vertical motion glasses on while you look at this. And you don't try to think about both of them at the same time, you'll get a headache. You just got to keep your thinking straight on what am I being asked to think about. Now I'm having you think about the vertical motion, which again is showing acceleration. What would the free body diagram look like for it while it's in the air? If AP exam said, here, right at this moment, freeze time, draw a free body diagram. What would that look like if this was the dot now for your free body diagram? Try it. It's in the middle of its trajectory. It's well gone from the corner of the table. And then someone freezes it, and on APC they say, here's an image of it. Draw a free body diagram for the ball now when it's in the middle of the air, just frozen in that moment of time. What forces now are we having to think about? Remember, what's the one that we can always add? Almost always. Right away for free body diagram. Yep, the weight of the ball, FG. What else? I will point out that since the ball is technically going along this type of curve like this, that in that moment, the air resistance force, there is a small amount in the real world, would actually be in the, because remember, which way is the velocity? Velocity vector is forward, tangent to the curve. Therefore, the air resistance force is in the actually opposite direction, 180 degrees from the velocity vector. They would never have you think about that because that's more of an AP Physics C. That's what you're doing. In your thing, they're going to have you start thinking about air resistance. So in AP Physics 1, they wouldn't mention that. I just wanted you to be aware of it, that it's real. It's a real force, air resistance. But for this, we wouldn't do it for this class. So what else do we add to this? Anything? Do we add any other thing to this free body diagram? The answer is no. The only other one we had before was the normal force from the table. It's not touching the table anymore. I just discussed the only other molecule that's touching it is air, which is the air resistance force, but they wouldn't want you to think about that. And again, it's a small amount of force. That little ball is very aerodynamic. It knives through the air pretty easily without much of an effect from the air. This is it, the force of gravity. There's only one thing that you would add. Therefore, what is the vertical acceleration? I want to point out, when I had previously written F net equals MA, I should have said in the X direction equals A in the X direction. When we were talking about horizontal motion, you have to think, what are the horizontal forces? We concluded there was none, and therefore the horizontal acceleration was also 0. Now, when you're thinking vertically, you can write Newton's second law again, F net equals MA, but you'd have to put a little y there to indicate now our glasses are on that are only seeing, come on, seriously? Our glasses are on that allow us to only see vertical motion. So this would be F net equals MA, but with little y's. I'm too aggressive, that's what it is. I'm too aggressive with my marker. I just have to have a gentle touch. You'd put a little y there for vertical motion. That's what the y is. It's just indicating that you're doing vertical stuff now. What is the vertical force that we identified? Fg. Erase some of this. We said the gravity force was its weight, m times g. Right? Well, I can't write in the black area, I guess. You'd say F times G equals m A. We're just writing this down, but instead of net force, you have to include whatever's in your free body diagram. It's just Fg. Fg equals ma. How do we calculate weight? M times G. Some of you would remember that maybe from a while back. mg is the way you calculate how much something weighs in newtons. So therefore, if we solve for the acceleration, m and m cancel, and we get a statement that says the vertical acceleration will be equal to g, because that's what didn't cancel out. So it's indicating that because the only force that's pulling down on it is its weight, it will accelerate at a rate equal to g. So that's true for all objects. It doesn't matter if it's a penny, if it's a mouse, if it's a human body, if it's a giant box. If whatever is falling has the total net force being equal to its weight, and no other forces are significant, then it will accelerate at a rate equal to g. That's the reason that all objects fall at a rate equal to g, regardless of what they are. Unless they're like feathers, then air resistance is not negligible. That means it's a significant amount of force on a feather compared to its weight. But otherwise, they all fall at the same rate. So I'd lastly say, because we're coming up on the end of this, what formula do you think we would use for this vertical motion idea? I'm gonna actually erase all of it because it's just too much. Last few minutes, what formula would we use to track the vertical position, which kept getting wider and wider? Remember that horizontally, when we were up here, I said that there was a formula for that, x equals vt, which models those positions, constant speed. If I said similarly, was there a horizontal formula for once it was in the air? Yeah, that worked for both sides. We already saw that it stayed at a horizontal constant speed on the table and in the air. Now we're asking the same question about, what about the vertical position? What formula would we use to model the fact that the vertical distance it falls each second is getting wider and wider and wider? We would write the same formula, y final equals y initial plus v initial y times t plus 1/2 at squared. Oop. It's the position formula just with y's, because the symbol y stands for vertical position, while the symbol x stands for horizontal position. What can we take the initial vertical position to be? Well, they had their xy axis right here. So at the edge of the table, what was its initial vertical position based on that xy axis choice? 0, starting at the origin based on that choice. What would the initial vertical velocity be? Remember that when it comes off the table, it's moving sideways with all horizontal velocity. This is the edge of the table. How much vertical velocity does it have at this spot that I just drew? You'd say none. All of the speed in that frozen moment is just purely sideways. Once it starts to fall, again, as we talked about before, there will eventually be some y component velocity. This would be vy. If the ball was really here, and this would be the vertical, the velocity rather. The vertical velocity is here, indicating it's got some downward component to its motion. You'd be like, yeah, of course, it's falling. But in this moment here, all horizontal velocity. And this represents the initial vertical velocity. There is no initial vertical velocity. It's all horizontal. It's 0. So what are we down to? Y equals 1/2 at squared. These positions are considered the y positions. All of these positions are called y. So I have y equals 1/2 at squared. That's the formula for predicting the vertical position at any given time t. What is a? What is the acceleration due to gravity? 9.8, because it's in free fall. What is half times 9.8? 4.9. So really the formula for predicting the vertical position, called YF, the final vertical position, at some point t, it's the vertical position t seconds into the fall. Just like up here, this is the horizontal position t seconds into its fall, t seconds into rolling. Depends on what the horizontal velocity would have been. Now we've got a similar formula down here, 4.9 t squared. So let's try it. How far will it have fallen in 1 second? How far will this ball fall vertically in 1 second? About 5 meters. 4.9 times 1 squared is 4.9 meters. How far will it fall in 2 seconds? 10 meters? Linear? No, we've concluded that the vertical is certainly not linear. This is not a linear pattern. If it was after 2 seconds at a distance of 10 meters below where it started, and then at 15 meters at 3 seconds and 20 meters, then you'd say, oh, that thing's falling at a constant speed. Things don't fall at constant speeds. You drop something, it just plummets and starts gaining speed faster and faster and faster. What would we get after 2 seconds? Almost 20 meters. So that pretty much, I'm gonna give you guys 2 problems to work on, only 2, that utilize the 2 formulas that are still on the board. The x equals v times t and the y equals 4.9 t squared. Those are 2 formulas that are totally related to the 2 problems I've assigned. I've already posted them. It's just 2 problems for tonight, but I still want you to upload them. Then tomorrow, I'm going to just give you problems. I'm going to just give you more problems to work on, because this is kind of me just teaching you the concepts and how you use the formulas. I'm just going to point out, it's only 30 minutes tomorrow, right? So we'll get 30 minutes of more problems in class. But make sure you upload those 2 problems before you leave. They're from the textbook. Remember that in the last reading assignment, I actually linked the file there for the first 3 chapters. So anybody who might not still have it, you can go back to that last reading assignment and click that link and you have it. But for other people who have it, it tells you which page to go to and the 2 problems that you'll see are related to this. Other than that, you guys have a great day. Take you as well. Take care. For those of you at home, let me say goodbye to you. See you later, Joey. Oh, what do you mean? I won't see you tomorrow? Oh, that's right. I'm totally forgetting. Yeah, forgot about that. See you next weekend. You're right. See you tomorrow online, though. So, guys, just give me 1 second. I would like to just say goodbye to you. I'm trying to just find you. It's so hard to find things in here. Oh, God. All right, there we are. Okay.
Did you see that they added breakout rooms to Google Meet?
Yeah, we just got the email today. So I'm super excited about that. So that we can start using them pretty soon. Yeah, I don't know how to use them yet, but I'm sure it can't be hard. The other thing is I hope you guys are considering the Pivot Interactives. I'd like to start using that next week. And once I start assigning things, then student would need to gain access to it. So email me if there's some reason you're unable to do it. Just explain to me and I'll see what I can do to help out. But otherwise, I'd like you to try to go on Pivot Interactives. Again, you would need your parents. It's $5 for the year. But it's a credit card necessary so that I don't think you guys have credit cards at this point. In fact, you can't have one until you're 18 years old. So other than that, you guys have any questions? You heard about my assignment for two problems tonight? All right. Bye, everybody. See you later. Have a
Bye,
great
Mr.
day.
Griffin.
Bye, Jaden. Bye, Caitlin. Bye, Carly. Bye, Zoe.